let's start with refraction, a little bit of background again. Then we're going to move forward with what refraction is. So refraction is basically the change in speed or the change in medium of the wave due to the change in medium of the wave, right? So the speed changes, due to change in medium, right? So what happens is that, for example, previously what we did was the speed of the wave increases or decreases. Today we're going to look at the specific terminologies associated with the change in medium. What would that be? So we did the seashore example. For example, like this, we realized that, let's say if this is the seashore and this is the layer of water around it, and this is where you're standing right now, by the way, right? Okay, so if there is a wave in water like this area would be known as deep region, and the areas with less depth will be known as shallow region, right? So when the wave actually travels from a deeper to a shallower region, it has been observed that the wave actually shrinks. So the wavelength from this point to this point, if you observe it this way, and the wavelength from this point to this point, they are different. So what has particularly happened is that when the medium changes, there should be a change of speed. So the formula goes V equals to F lambda. We know that the frequency is constant. And why is the frequency constant? Because it is controlled by the source. Whoever produced the wave will be responsible for the frequency of the wave. So since the wave is coming from this side, it could be produced due to the air, could be produced due to the changes of the tectonic plates. So whatever caused this wave to move or to originate in the first place, that is what is going to control the frequency. We can't control or we can't change the frequency from external factors. So for the sake of discussion, what we say that V is now only proportional to lambda, we are eliminating, or we are not thinking about frequency anymore because it's constant. Okay, so visually what we see is that the wavelength has reduced. So if the wavelength has reduced, what should have happened to the speed? The speed should also have reduced because they are directly proportional. But they will decrease, or you can say they both will decrease in such a way that the frequency will still be the same. I'm going to give you a mathematical example of this one, how to visualize it or how to think about it. Is that, for example, if we had the formula V equals to F lambda and we want to find the frequency, so we are left with V divided by lambda. Let's consider two possibilities. Previously, if the wave was not observing a change of medium, so let's say the speed was 10 meters per second and the wavelength was the wavelength was 5, right? So we got a frequency of 2 hertz. Now after crossing the medium, the wavelength has reduced and so has the speed. So this time around, let's say the speed is 4 and the wavelength is 2. So again, our answer is 2 hertz. So what's happening is that once you observe a reduction in wavelength, the speed will also decrease in such a way that the frequency will remain the same. So if we can observe over here that the velocity has decreased and the wavelength has also decreased, but by such an amount that the ratio that gives us the frequency still comes out to be the same.
So this is basically just proves that the frequency is a constant value.
Yeah, frequency is going to be constant for this system when the wave is undergoing refraction. So something similar happens. Okay, so this is just one perspective how to look at it. There is another perspective how to look at this, and that would be through a ripple tank. Do we remember what is a ripple tank and what does that look like?
Yeah.
Okay, so we're going to go back to the ripple tank and we're going to try to visualize what's happening with the wave. So let's say this is our ripple tank, and this is, so previously what we have done is we have moved from deep region to the shallow region. Okay, this time around we're going to move the opposite way. We're going to move from shallow region to the deeper region. So which region are we exactly referring to as the shallow one and which one is the deeper one? So if the wave is originated from this point by the oscillator of the ripple tank, then this is how the wave is actually going to be produced, and it's going to move towards this side. Okay. So since this has less depth, this side of the wave would be referred as shallow, and consider this just as a hindrance or a block of wood or a block of or just a brick placed inside the ripple tank at the lower side, so that water has less area over here to move. And on the other hand, there is no brick, there is no hindrance, water has a larger area to move. So over here it's moving from shallow to a deeper region in terms of its height from the top surface, right? So in this way, or in this implementation, what we saw was that if this is the wave, the moment it crosses the boundary that is going to be at this point, the moment it crosses the boundary, the speed increases and so does the wavelength. So if it is this way, the speed would increase and the wavelength would also increase. Now there are two things happening at the same time. Velocity cannot be calculated just by looking at the wave. You have to take measurements of the wave. But wavelengths can visually be confirmed just by looking at the system. So if I can see that this is my wavelength before the change of medium, I can very well see that this is my wavelength after the change of medium. So the wavelength has increased. So if visually speaking, this is what I can see with my eyes, if the wavelength has increased, I can very well say that the speed must also have increased. So if I had known the speed of the wave and in this region, let's say the speed was 5 meters per second, I can predict that in this case the speed would be greater than 5. It could be 6, could be 7, could be 10, 100, 1000, I don't care. The speed would be greater than 5. Okay. So this is our refraction from shallow to deep. This is what it looks like from the side. This is what it looks like for deep to shallow. This is just an example for the seashore. It could be the other way around as well. It could be from shallow to deep, and it would have the reverse trend. So this is one way to observe that. This is another way to observe that. Now let's try to visualize it from the top. Let's say that you are observing from this location with your eyes from the top. So what you're going to observe is that if this is your ripple tank, then you will observe the wave fronts to be like this. These will be your wave fronts, right? And let's say that this is our change of medium barrier. This is where we encounter the brick in 3 dimensions, or moving from 3 dimension to 2 dimension. This is where we encounter the brick, right? So let's say that if you were moving from shallow to deep, I'm going to draw this with red color. I would see that the speed would the speed would increase and the wavelength would also increase because they are both proportional. So I will see an increase in my wavelength visually. So if the wavelength, this is what the wavelength was before, this is the wavelength after. Similarly, if I'm moving from deep to shallow, what's going to happen? Wavelength would decrease, velocity would decrease, and visually speaking, what should I see? This is the change of barrier. I'm just drawing it deliberately, a change of barrier, so that you can see that over here. Otherwise, it's not visible like this. So for example, if the wavelength was like this before crossing the barrier, after crossing the barrier, the wavelength would decrease and it will become shorter than before. So this is what we can see with our eyes, and this is what we can confirm by just looking at them. We cannot give a value for the velocity, but I can very well say, looking at the wavelength, I can predict, I can comment about the velocity of this wave. Do we understand this point?
Yeah.
Alright. Now let's try to do this in a different way. The type of question that the examiner would give you is when the barrier is at an angle. For example, right now the barrier is perpendicular to the wave fronts. The wave is moving like this and encounters the change of medium, and then we are expecting something to happen. What if the wave encounters a barrier like this at an angle and the wave front is actually moving like this? I will also show this in a video as well, but for now let's discuss it over here. I'm not touching these wave fronts over here, although they would be touching with the change in medium or the change in barrier, like so. And let's draw another diagram for the same purpose with a different mindset. So let's say that over here the wave is in shallow region, and over here it will be in deeper region, right? So the wave is moving like this, and over here the wave is again moving like this, but over here it's in deeper region and is moving towards shallower region. Now we know that when the wave moves from deep to shallow, we expect its velocity to decrease and wavelength to decrease. And when it moves from shallow to deep, we expect its velocity to increase and wavelengths to increase. This is what you're supposed to memorize or keep that in mind. So if I have to show the wavelength increases or the increase in wavelength, for this case, let's get to this later, but let's try to do this one first. This one is easier. So the wavelength has to decrease, or the wavelength reduces. So the wave basically bends like this. The wave bends like this. And why is that happening? We will discuss that later. So if this was our wavelength before it encountered a change of medium, this is our wavelength after it encounters a change of medium. One more thing I would like to add is sometimes when you were in smaller grades, you may have heard that refraction is the bending of light or the bending of wave. We can see that bending over here, that first the wave was actually traveling like this. It would have moved in this way directly eventually, but now the wave is moving like this. So the direction of the wave has also changed. Do we understand this idea, visualization?
Yes, yes.
I will discuss why this is happening this way, but let's get ahead with this one. So I understand that for this case, the wavelength should increase because the speed is going to increase. So there is only one way that it could have happened. It is this way. The waves are actually moving this way. So what's happening in this case? The wave was moving in this direction, but now the wave is moving in this direction. So it has also changed its direction. If I compare this by extending it forward and extending it backward, so this is where it was initially, this is where it's now. So it has changed its direction a bit. Do we understand this and realize it? Yes?
Yes.
Okay. So what's with the wavelength? This was my wavelength previously, and this is my wavelength now. Visually speaking, just by looking at it, I can confirm that my wavelength has increased. And I can also confirm that the speed should also have increased because they are directly proportional. So this is what I see in real life, and this is what gives me the confidence to comment about the speed. Do we understand up to this point?
Yes.
Now let's discuss what's actually happening and why it's bending. What's actually the problem? You see, if this is the barrier that I'm talking about right now, I'm only going to draw two wave fronts, because if I draw more it gets a little messy. Okay, so this is my wave front. I am drawing the wave fronts in this manner, keeping in mind that it looks like that there was no wave front over here. So I'm representing it by dotted lines like this. Okay. This is where they should have been if there was no barrier. Do we agree with that? If there was no barrier, this is where they should have been, right?
Yes.
Okay, so now they did encounter some barrier. They did encounter some change. What has happened? I'm discussing this with deep to shallow. So this is my deeper region. This is my shallow region. I should expect a reduction in velocity and a reduction in wavelength. What's happened? Basically, the particles of the wave front are still moving towards this side. But this portion, this lower portion bit of the wave front has encountered the barrier before or at first than this part of the wave. Is that so? The lower part of the wave has met with the barrier before this part could even have the chance to meet it. Do we understand this point? Right? And since I've said that it is going to slow down, or it's going to eventually cause this wave to slow down, what has happened is that just imagine that these were water particles. These were all runners, people running towards the finish line. The people or the objects that encountered this change in barrier have now slowed down a bit. Similarly over here, the same people or the same water particles are running, but some who have encountered a change in medium have lagged behind. So what has happened is that, ideally speaking, if there was no barrier, this is where they should have been, but they're not. They're actually found at this location, similarly to this one, similarly to this one, and so on and so forth. So what we see with our eyes is that wavefront becoming like this eventually. wavefront becoming like this eventually. What's happening is that the lower part of the wave encounters the medium first, and their particles actually slow down, and these particles are still running at their full speed because they have not encountered the change of medium yet. Do we understand this point?
Yeah.
Right? So this is what's actually happening at the back end. This explanation is basically a bit high level than O levels. You're not required to provide this explanation, but I've just explained this to you so that you don't have to remember what's actually happening. You can actually figure this out on your own at every place. Similarly over here again, this is where the wavefront should have been, but it's not, because this part of the wavefront has encountered the barrier first, so these particles have lagged behind. They have slowed down before these particles had the chance, because they have not encountered the barrier or the change in medium yet. Is that acceptable? Right? The same thing is happening over here, is that ideally speaking, this is where the wavefront should have been. But since it speeds up after changing the medium, in this case, the particles should have been at this place, but they're not. They're actually at this place. They're running faster than its original wavefront, where the runners are actually this place. But the ones that have encountered the change of medium, their runners are actually at this place now. So that is why it's bending like this, and this one is bending like this. Do we understand this explanation? All right, good. So now we're going to move towards the video for this refraction. Okay, so this is the reflection. I think we did that, right? Do we remember this visualization? Yes?
Yeah, yes.
Okay. Okay, so do you see that the wavefront previously, over here, if I look at the wavefront, just for the sake of observation, this is my wavefront before it entered the medium, right? So what's happening when it changes this medium? Do you see that the wavefronts are getting closer?
Yes.
So what can I comment about the change? You see, he did not introduce a change in medium on this side, but he did on this side for a comparison, right? So if this is my wavelength before it crosses the medium, and this is my wavelength after it crosses the medium, what can I say about the change in medium? What medium should this be? This should be deep, and this should be shallow. How did I reach this conclusion? I know that V and lambda are directly proportional. I see visually that the wavelength is decreasing when it crosses the medium. So the speed must also be decreasing, which means it is moving from a deeper region to a shallow region. Is that acceptable? Do we understand this?
Yeah.
Okay, okay. So let's keep on playing the video. Shorter wavelength, and of course, okay, so this is what is happening when the barrier is at an angle. Can you predict what type of refraction would this be? You see, the wavefront previously is like this, okay, and it's becoming this. So the wavelength previously is large, and the wavelength after the change in medium
So
is
it's
small.
from deeper to shallower because
Yeah.
these particles is going down fast.
Exactly. So this is again deep to shallow, because the speed is decreasing and the wavelength is also decreasing. This is what we can see in this
And you
diagram.
can-
Yeah.
Yeah, and you can also see the wavelength is decreased as well.
Yeah. Yeah. Okay. Again, the same visualization. Now, what can you say about this one? Can we see that the wavelength is increasing in size from this point and this point? And over here, we see an increase in the crest to crest gap. So over here, the wavelength from changing medium is increasing. This is what you can see with your eyes. And what can you use this information? How can you use this information to conclude? You can say that if the wavelength is increasing, the speed is also increasing. Why? Because the wave's velocity and wavelength are proportional to each other. The reason being because the frequency is constant, and the frequency is controlled by this oscillator that we have over here. This is the oscillator that we have here. So whatever oscillations or whatever vibrations it's producing at any given moment, we can't change that because it has a fixed value. Do we understand this point? All right, all right. Okay. So,
Also, so the bending effect of refraction only occurs when the surface and the wavefront are at an angle with each other.
yeah, the bending only occurs when they are at an angle. Otherwise, if they are perpendicular,
Okay.
you won't
Mhm.
see the
Yeah.
bending. Yeah, but this is still refraction, right? Because a change
Yeah.
of medium has caused a change in speed, so this will also qualify.
Bending,
Yeah,
yeah,
so
doesn't
that
define refraction. It's
exactly,
inconsistent.
bending is a special case for refraction. It's not a condition for refraction.
It just means certain parts
Yeah,
are slowing or
yeah,
speeding
yeah,
down, it's changing speed with
yeah,
basically.
yeah, yeah. So what's happening over here? Can you predict? So smaller wavelength is increasing to a larger wavelength. It should be moving
Mm-hmm.
from a shallow region to a deeper region, right? And it is
Mm-hmm.
bending away. It's bending away from the wave. Okay. Similar things are
Mm-hmm.
happening at this point as well. Okay, these are just different implementations now. So the next topic is diffraction. This is new for O levels. It was only available in IGCSE, but now they have included in O levels because diffraction is a major part in A level physics. Okay, so diffraction is simply bending of wave around an edge. What is that? For example, if we see a single edge like this and we see a single edge like this, what's happening is that if we encounter a wave front or a wave coming towards this gap, as it passes through the gap, the wave actually becomes or starts to have circular wave fronts. Now, this is new. This is a new phenomena. This is something new. This is beyond our expectation. This should not have happened, but it does. So the wave basically actually bends around the edge outwards. The wave front that is exactly in front of this gap does not bend. So it is going to remain straight. It will remain straight, or it appears to be straight, but the wave that is around the edge appears to have bent, and of course will keep on continuing like this. Now, how do we see that around the edge? For example, if this is the wavefront coming towards the edge, so as the lower part, this is just for your reference, you don't have to draw it this way, this is just for you. This part where we see that there is no edge, over here the wavefront continues with the same parallel wavefront, but around the edge it has to bend, right? So we continue these wavefronts like this in a curved manner and join them with the edge. So this bending around the corner, this is diffraction. Do we understand this idea?
Mm-hmm. Yeah.
All right. So this depends on two things. The first one, I'm just going to write this down directly. We have diffraction. Bending, or the extent of bending effect, depends on two things. First is the gap width. When we say gap width, this is what we're talking about, the gap of the of both edges, right? And the second factor it depends on is the wavelength. So for diffraction and wavelength, they are directly proportional. So diffraction is directly proportional to wavelength, but diffraction is inversely proportional to the gap. What happens, or what it says is that if you increase the gap, the diffraction or the extent of curving of this wavefront will decrease. Okay, and I will show this to you in the diagram. Over here, it shows, or it says that the wavelength directly proportional to diffraction. If you increase the wavelength, the diffraction or the extent of bending will increase. Okay, do you understand this point?
Mm-hmm.
Now I will show you
So,
just a moment. I will show you a visualization for this that will make it a little bit better. Okay. First, let's try to visualize what the wave front actually looks like. Can we understand the wave fronts? A series
yeah.
of crests and troughs, right? So the lighter parts are crest, and the darker parts are troughs, right? Okay. So if I bring this back to see what's going to happen when they pass through the gap, try to observe what's happening with the wavefront. Is it becoming circular?
Yeah, you can also see the fact that the part that directly goes in between the
Exactly.
gaps
It
stays
doesn't bend.
straight and the
It
rest
stays same, yeah. So if I increase the gap, it becomes even more evident. So the part that is exactly in front of the gap, it stays as a parallel wavefront. It stays straight. The only wavefront that actually bends is actually that encounters the edge. Okay?
Yeah. So a larger gap means less of the wavefront is actually
Exactly.
going to be.
Exactly. Right? So let's reduce the gap and see what happens now. So now the bending has increased to much greater extent, and it appears that it has converted, or it has caused this wavefront to become completely circular. But then again, if I just extend it up to in front of this one, the gap, I will still find it to be somewhat straight. But since it's such a large curve now, it's such a large arc, that it appears that it is still circular. Okay?
Yeah, yeah.
Do we understand this point?
Yes.
So this is diffraction. Passing of my wave fronts through a gap cause them to become circular. Okay?